Welcome back, APCSA students. This is the second video related to Lecture 3 slides. In this video, I'm going to talk about order of operations or precedence of evaluating expressions, a little bit about tracing, some information on math and integer classes, and also on arithmetic overflow. So let's get started. So precedence is the fancy term for order of operations. So just like in regular math class, a lot of the order of operations is the same. Parentheses go first. After that, multiplication and division. And now we have this modulus operator. And if you think about it, it is related to division. So it has the same precedence as multiplication and division. And those values are higher precedent than addition, subtraction. So the higher the precedent, the sooner you perform it. So first do your parentheses, then do multiplication, division, and modulus, moving from left to right, just like in normal math class, and then do your addition, subtraction. So just a note, if you look at this last problem, it looks like they wanted to do 1 plus 3 first and 4 minus 2 first and then multiply. These spaces mean nothing. If you really wanted to group them that way, you would need to use parentheses in order to get the 1 plus 3 to happen first. So in this last example, it does multiply 3 times 4, and we get 12. Then we add the 1, and we get 13. And then we subtract the 2, and we get 11. So normal order of operations, we have a couple examples here that step through step by step how they're being done. So notice that all of these operands are integers, so it's 1 times 2 plus 3 times 5 mod 4, but all these values are integer values. So these are nice charts that you can work through to see what is happening first, what is happening second, what happens third, what happens fourth. And when you are evaluating the expressions on paper, you want to do a similar format in your mind, whether you don't necessarily break it down this detailed on your paper, but this is how you need to be thinking about these. And the computer does the same, it just does it very, very fast. So again, these are all integer values, the 1, the 2, the 3, the 5, the 4. I can see that they are integers, the 8 and the 9, they are integers because there's no decimal value shown. So similarly, these could have been variables that were declared as ints, and they stored the value 1, 2, 3, 5, 4. So those could have been variables that I'm multiplying together. I need to know if the variables are ints or doubles, because as we saw in the last video, once I introduce doubles, my result is a double. So I need to know when I have decimals introduced. So here's some examples of decimals being introduced. And we saw also in the last video that if I don't want this negative 42 to be seen as an integer, I can simply add a 0.0 on it. And that makes it a double or a decimal value. And so then my result from the math will be a decimal as well. So when doubles are there, the result's a double, but the precedent is the same, the ordering is the same, and again, we will not be doing modulus with doubles. We will only do mod with integer values, but after the modulus is done, there may be some doubles that are introduced. So here's an example with doubles or decimal values. So we can see that still so multiplication, division, and modulus happen first from left to right. So we would do the 2.0 times 2.4, and we would get the result as a double. And then we would do the next multiplication, and then we would do the division, and finally we would add those two operands. So we want to keep that order of operations, especially when we have to trace on paper to give the result when we can't rely on the computer. So the challenge comes in when we start mixing types, when we start mixing integers and doubles. So in this first example, 4.2 times 3, 4.2 is a double, 3 is an integer. I can tell by looking at it. Again, that 4.2 could have been stored in a double variable, and that 3 could have been stored in an int variable. The point is, when I multiply a double and an int, the result is a double. So there's no way that I can store that double value in an integer variable. So I need to be aware of what types I'm working with, and especially since we saw in the last one that integer division causes you to truncate decimal values, so we want to be aware of what we have at each time. So in this first example, moving left to right, again, 7 and 3 could have been two variables. Once I divide them, the result is an integer. I can see here they're ints because they don't have a point or a 0.0 after them. So the result of 7 divided by 3 is 2. It's not 2.5, it's just 2. That 0.5 is lost. Then I'm going to multiply 2 times 1.2. Now I've got a double introduced. So the result of 2 times 1.2 is going to be a double. It's not going to go back and get that 0.5. That 0.5 was lost from 7 divided by 3. Then the next step is to do the go over and do the next division. So 3 divided by 2, those two operands are integers, so the result is an integer. The final operation is that 2.4 double plus the 1 integer. As long as a double is somewhere, my result is a double, so I get 3.4. In the second example, multiplication division happens first from left to right, so I do 10 divided by 3. Both are integers. The result is an integer of 3. Then I do 3 times 2.5. One's an integer, one's a double. The result is a double, so 7.5. Then I'm going to do 6 divided by 4. Both are ints. The result's an int, so I get a 1. Then I'm going to start doing the addition subtraction from left to right. And again, I'm doing the same thing. Oh, both are doubles. The result is double. Then I've got a double minus an int. The result is a double. So as long as a double's somewhere, the result's a double. But in an int, the result is an int. I'm going to show an example of code tracing in a Java program. So if you were going to do this on paper, I'm going to show in the program how you can go through step by step, but that is, I would do this step by step on paper. I'm just not going to bring the paper up for now. I'm going to show you how to use the debugger to do it. So I'll make another video later on more specifics of using the debugger, but I can show for this example the step-by-step nature. So here is that same code that is from that slide. So I've put a stop sign here because I want the program execution to stop there when it gets to that stop sign. So you can see it's stopped here. I have all this kind of stuff. And I'm going to step through the line that's highlighted is the line that's going to be executed. And I'm going to hit this down arrow and it's going to execute one line of code at a time. So after it executes this line of making an integer variable x that gets a value 0, you can see here is my local variable x and it has the value 0. Then I'm going to go through and I'm going to make a variable y and it's going to get the value 5. Make a variable z and it gets the value 1. So when you're evaluating these expressions, and these are all simple expressions, here I want x plus 1. So x right now is 0, so 0 plus 1 is 1, and I'm going to store that in x. So when I hit the down arrow, you're going to see this value for x change to be a 1. So if you had this on paper, you would cross out the 0 and put the 1, because remember these variables can only hold one value at a time. Now I take the current value of y, which is 5, I subtract 3 and I get 2, and so the variable y gets the value 2, so I'm going to see that change to a 2. Now I take the current value of x and the current value of z, they're both 1, I add them together, I get 2, and the variable z gets the value of that addition, which is a 2. So when I hit the down arrow, we're going to see z change to a 2 as well. Take the current value of y, it's 2. The current value of z is 2. Multiply them together, I get 4. X gets the value 4. So I'd cross that out on my paper and give x the value 4. Y right now is a 2. 2 mod 2 is going to be 0. Because 2 divided by 2 is 1 and the remainder is 0. And so I want the remainder from this. So y is going to get the value of 0. And then finally, z is going to equal what it was before minus 1. So z equals 2 minus 1, or z gets the value of 2 minus 1, so z gets the value of 1. And so now when I print these out, we're going to see that 401. So doing the same sort of step-by-step on paper again and crossing out, making a t-chart and crossing out these variables is highly recommended for tracing. And I know you've not been given paper to do this, right? You've not been given the printouts, but I would recommend doing that since the AP exam is on paper, getting used to seeing it on paper. So the last piece on this video is just introducing a couple of extra things we can throw into our math expressions using from the math and the integer class. So the math class has some math methods, math functions we can use. You can see here ABS, you can probably tell it's absolute value. SQRT is going to give me the square root of a number. POW is something I can use to raise a number to any power. And again, any of these numeric literals in here could have been variables. The math class also has a constant called pi that will has a good estimate of pi, so that we don't need to type in 3.147 or whatever it is, 259,759. And then, so that's out of the math class we will get that. And the integer class has this min and max value that we'll look at. And what it tells us is integer.min value returns the very smallest int value you can store in an int variable. And integer.max value gives you the largest int value you could store in a variable. So I'm going to show you this in the code. So part 5 down here starts with, and I have a couple things in here, but I'll run it and go up to the top first. So here you'll see the absolute value of -10 just gives me 10. It just returns the positive. So it's a silly example here, right? We could have just said print 10. Why would I say print math? But pretend there's a computation, a formula, and for some reason you need the absolute value and it's all numbers stored in variables and you don't even know if it's a negative or not. This could have been a variable and you just return the absolute value of it this way. So get the square root of 9, we get a 3.0, so that's the square root of 9. 2 to the 5th is 2 times 2 times 2 times 2 times 2, we get 32. Math.pi, this is the estimate. This variable, this constant is already storing the estimate for pi, so we can use that in any calculation that uses pi. And I just want to show you that these are just evaluate to numbers, so they can be part of a bigger expression here. So I'm getting the square root of 9 is 3, and you can think of it as parentheses, right? You see parentheses there, so you would evaluate this as early as you can, unless there's something inside of there to evaluate first. So square root of 9 would be 3. Then I would go and I'd do 7 times 5 is 35, because multiplication would come next. And so then I would add the 3 plus the 35 and get the 38.0. It turns out that this method returns, or that this method always returns a double. So that's why the answer looks like a double. You don't need to worry too much about that. I just want you to get comfortable seeing these and using these. Here's one where the area of a circle would be, so a circle that with radius 5.5, you can see how you can use these math methods and math constant to calculate area. So I have pi r squared here, and I can print the area. So here's the area of a circle with radius 5.5. And then that integer min value, max value is right here. So this is, if I make an int variable, int x equals some value, this is the smallest value I can put in it. And this is the absolute largest value I can put in it. And so these are just nice to look at for now, but we will use these periodically later, these constants. There are uses for them, but it's just a good thing to be aware of right now. So because int max value, integer.max value,